Yeah, thank you. So before this VHDL and Verilog, that is these before these two hardware description languages, the designers used to design the entire circuit using the pen and paper, and they use it and they use that schematics to design all the chips physically. So after introduction of this EDA, after introduction to this EDA tools, that is VHDL and HDL, so it became very easy for the designers to describe all the hardware descriptions of the chips. So the designers now they will basically code in Verilog or VHDL, and they will simply generate a gate level netlist from the Verilog and VHDL, and using that netlist, placing and routing will happen and so on. So by this way, the Verilog and VHDL are very useful for the designers. So now let's see about. So is this pace is clear, and is this type of explanation is okay for all?
Yes, sir.
Okay, thank you. So here that design now let's discuss about this design flow. So this design flow is very important, like in interviews also they will ask to describe about the design flow. So remembering this design flow is very important, so I will write the design flow here. So in the design flow, the first step is design specification. So this step is nothing but basically specifying the design. Like for example, you know, full ladder and half adder, right? So for example, if we take a full ladder, the specification, the design specification describes the behavior of this full ladder. That is, it has three inputs and two outputs. These three inputs may be some A, B, and carry in, and the outputs may be sum and C out. So, and in this full adder, we don't know what there is inside in this full adder. So we are just specifying the behavior of this full adder, that this full adder will take the three inputs and it will add the three inputs and it will generate the sum and carry. Sum is nothing but A plus B plus C in, and we will get a carry. So in the design specification, we are just simply specifying about the design. So in the design flow, our first step is specifying the design, and the second step is behavioral description. That is describing about the behavior of the module or the design, and the third step is RTL description. Here our Verilog and VHDL comes into play. That is, here in this step we will write the code for the design in Verilog and VHDL. So in this step we will write all the codings, and after this we have, sorry, I think this frame is not sufficient. So from tomorrow I will try to use another type of interface for writing. So for today, please adjust for this. So after this RTL description, we have functional verification and testing. So coming to this functional verification and testing, in this stage we will check for the functionalities of the design. That is, whether our desired functionalities are being correctly implemented by the design or not. In this step we will check for that using some EDA tools available in the market. So we will check for the functional verification, and after that, if we get satisfied with the functional verification and testing, we will do logic synthesizing. Basically, in this step, after functional verification, the code which we have written in our HDL will be converted into a synthesis, will be converted into a design. We will see in our upcoming sessions how we will do synthesis and all. So the code which we have written will be converted into a design in this step, in the logical synthesis. And after that, for this logical synthesis, a gate level synthesis will be generated. Gate level synthesis will be generated. So in this gate level synthesis, generally this gate level synthesis is this logical synthesis and gate level synthesis, this all are done by the tool only. So no need to worry about, only we need to worry about writing the code. So this gate level synthesis will describe how what type of gates will be there in the design, and extra stuff we will discuss it in our upcoming videos. And after this gate level netlist, we will have logical verification and testing, and after that we will have floor planning. So basically, in yesterday's session, Swaroop was saying about this backend. So floor planning and physical layout. So this is all the backend work. So after that physical layout, we will have layout verification, and finally implementation. So this is the basic design flow of our VLSI. So this is very important for interview aspect also. So please note down if you want, or else we can move on. So is it okay for everyone? Hello?
Yes, sir.
Yeah. Are there any doubts regarding this? Or we can proceed further?
We can proceed, sir.
Okay, thank you. So give me a minute. So yeah, now let's discuss about importance of HDLs. So where these HDLs are used, that is, we have two languages, right? VHDL and Verilog. So for these sessions, we will discuss about only Verilog, and we will see later about VHDL. So for now, Verilog language is described at a very abstract level. That is, uh, even a guy who is not aware of digital design in depth, he can also, with a minimal knowledge, he can write the code, and he can synthesize the code. And designers can write their RTL description without choosing a specific fabrication. So there is, so we can write the code, so we can write the Verilog code independent of fabrication technology. This is a very important point. So, so we can write the Verilog code without depending upon the fabrication technology. We all know, right? We all know that there is different types of fabrication technologies available. So independent of the fabrication technology, we can write the Verilog code, and logic synthesis tools can automatically convert that design to any fabrication technology. So if any new technology emerges, also designers no need to redesign the circuit. They can simply input that RTL description to the logic synthesis tool and create a new gate level netlist. So if we are using, for suppose say 5 nanometer fabrication technology, and we have written a code at this time, like we have written our RTL code at this time, and we have generated our gate level netlist for this RTL code, and if we have generated our gate level netlist for this code, and if the, say if the fabrication technology has changed to 2 nanometer, so there is no need to change our circuit completely. Just we need to again give our RTL code to our logic synthesizer, so it will automatically change our RTL code to gate level netlist. So this is a very big advantage of this Verilog. And by describing the HDLs, functional verification of the design can be done early in the design cycle. So in the previous slide, here after RTL description only, we are doing functional verification. So if so because of this RTL description, so after this, after writing the code only, we can do the functional verification. We no need to wait for the entire fabrication process to get completed, and after that, there is no need to check for the verification. We can check after writing the code only. So this is also the advantage of using Verilog. And if there are and we will also do simulation, like after writing the RTL code, for this RTL code we will write the test bench. So in this test bench we will check for the design is working properly or not according to our specification. We cannot check completely, but up to some extent we can check our design is working or not properly by writing a test bench. So by this we can check whether our specified design is working with our design is meeting our specifications or not. We can check with this RTL. So this is also an advantage, and this will cut down the design cycle time. This will basically save the time, because we have if we want to check after the fabrication, entire fabrication is done, then it will take long time, and if there is a bug found in the chip, then it will be a problem. Then we need to again change the entire design, and we should again check for it. So this RTL made us life easy. So, and this HDL is also analogous to computer programming, like a textual description with commands is an easier way. So it is an easier way to develop and debug the circuits. So these are some of the advantages and uses of Verilog. So we will directly jump into the RTL coding, like what we will write and how we will write. So in Verilog language, for writing any code, we should first declare a module followed by end module. Module followed by the name of the module. So the code, and in middle we will write the code. So without a module and end module, we cannot write a code. And this module is a basic building block in the Verilog. So a module can be an element or a collection of lower level design blocks. Typically, like a module provides the necessary functionality to the higher level blocks. For example, if we you all have the idea of digital electronics, right? Electronics. I will take a basic example like half adder. So basically, a half adder, what it will do, it will have two inputs and it will have two outputs, sum and carry out. So if we want to design this half adder, then for writing the Verilog code for this half adder, we will first declare a module followed by the name of the module. The name can be okay. So the name of the module can be anything. It can be anything like it can be A, B, C or something. But for avoiding confusions, if the design is half adder, we will generally use the name of the design like half underscore adder like this. And we will write the code in this module, and after that we should end this module. So this is a basic syntax for starting the Verilog code. We will declare a module and followed by module name and followed by the code and end module. Wait a minute. So this is a basic syntax. So module followed by module name, and the code will be written inside a module, and we will end the module. So the code which is written outside the module is not synthesized by the simulator. The simulator will understand only the code which is written inside the module and end module. So this is the basic building block. And yeah, up to here, is there any doubt? Is it clear?
Yes, sir.
Okay. So now we have four types of modeling in Verilog. So first one is behavioral, and second one is data flow, and coming to third one, gate level, and fourth one is switch level. So Verilog supports these four types of modeling. So now let's discuss about these four types of modeling in detail. So coming to behavioral model, in behavioral model, uh, the designer simply, wait a minute. So in case of a behavioral model, the designer simply gives the behavior of the design. Like for example, our half adder example, what this half adder will do, it will take two inputs and it will generate two outputs. So the designer will basically write the code describing the behavior only. He will not go in detail. He will write that it will take two inputs and it will generate two outputs accordingly. By following a similar fashion, he will write the code, like he will describe the behavior of the design. So in this type of behavioral modeling, the designer will describe the design using the behavior of the given design. And coming to gate data flow. So in the data flow modeling, so in the data flow modeling, the designer will describe how the data should flow. So basically in this type of modeling, the designer will specify how the data should be flowed, where it should be flowed, Like he will describe the design in the terms of data flow. So we will discuss this modeling in detail in further sessions. So for basic idea, just remember that in data flow modeling, he will describe the design in terms of data flow. And coming to gate level netlist, and coming to gate level modeling. So in this type of modeling, the module is implemented in terms of logic gates and interconnections between the gates. So in this type of modeling, the design is implemented in terms of logic gates and the connections between them. We'll also discuss about this gate level modeling in detail in upcoming sessions. Wait a minute. So yeah. So in this type of gate level modeling, the design is implemented in terms of logic gates and the connections between them. And last one, the switch level modeling. So in this modeling, a model is implemented in terms of switches, storage nodes, and interconnections between them. So these are the basic four types of modeling. This is nothing but how a code can be written. So these four types of modeling will describe how a code can be written. A designer can use a behavioral modeling, like he can just describe the behavior. He can write the code by describing the behavior of the design, or he can use the data flow modeling by describing how the data should flow like that. And he can also use gate level modeling, like the design is implemented in terms of logic gates and switch level, and the designer has the choice to mix all of these modelings, all of this behavior, and he can write the RTL code. So these are the four types of modelings in that Verilog supports. So is this clear? We can we move further, or are there any doubts in the module? Let's take again this half adder example. If we want to design this half adder, let's say the design, the specification we got, in that specification we have, for this half adder we have inputs as A and B and outputs as sum and cout. So we have got this specification. So now I am not dealing with any behavioral modeling. I'm trying to just explain the ports. I'm trying to explain the concept of ports. So while starting with the design, we will get this design specification about this half adder, and we will also come to know that the functionality of the half adder is to generate a sum and cout. A and B are the inputs for this design. So these are the inputs for the design, and sum and cout are the outputs for the design. So we want to start writing the code for this half adder. So we will declare a module, and we will declare some name for this module, let's say HA. And there are two ways to declare this ports. Wait, let me take another slide. So we will write a module, and we will write a and we will declare the name of the module, let's say HA. And there are two ways to represent the port. So let me take the first way to represent the port. So for this half adder, what are the inputs we have for this half adder? A and B are the inputs for our half adder. So we can write A, comma B, and after that What are the outputs we have? Sum and Cout. So we can write sum comma Cout and close this module followed by semicolon, and here we will write the direction input A, input B, output sum and output carry, and followed by some code and ending the module. This is very important. So here we are describing that for our design HA we have two inputs called A and B and two outputs called sum and carry. So the tool will come to know that for our design HA we are having two inputs as A and B and two outputs as sum and carry. So this is one way of representing the inputs and output ports, and there is also another way to represent these ports. We can use any of this model, so we can write the module followed by module name followed by, in this only we can represent the input and output. Input A comma input B comma output sum comma output carry, closing this followed by coding and end module. So this is another way of representing the ports in our module. So this two way we can write, but I generally prefer the second way of writing. So here we can use module HA followed by input A, input B, output sum, output carry, and ending the module. So this is a way, these are the two ways for representing our modules.